Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to lesson 14. This is solving inequalities. Very similar to solving equations, you just have to be careful when you divide by negatives or multiply by negatives. Okay, so this starts out with a classwork exercise, so pause the video, see if you can do this page, and then come back and see how you did. All right, here we go. Number one, consider the inequality, x squared plus 4x is greater than or equal to 5. Sift through some possible values to assign to x that make this inequality a true statement. Find at least two positive values at work and at least two negative values at work. So I'm just going to solve this as an inequality, and if your two values you chose are in my solution set, then you got the right answer. So if I'm going to solve this, I would take x squared plus 4x is greater than or equal to 5. I'm going to move the 5 over to the other side by subtracting, and that will give me x squared plus 4x minus 5 is greater than or equal to 0. Then I'm going to factor this, and I'm going to put an x here, I'm going to put an x here, and those two factors have to be greater than or equal to 0. Factors of 5 that add up to 4 are 5 times 1. In order to get c to be negative, they have to be, one has to be positive, one has to be negative. In order for the middle term to be positive, the bigger number must be positive, so therefore the smaller is negative. So I get x plus 5 times x minus 1 is greater than or equal to 0. Well, if this equals 0, then x would have to be greater than or equal to negative 5. I'm sorry, not greater than or equal to, less than or equal to negative 5. And if I add 1, or if I set this equal to 0, x minus 1 equals 0, then x would have to be greater than or equal to 1. So if you chose a value less than negative 5, negative 6, negative 7, negative 8, and so on, you have the right solutions for two values. If you chose values such as 2, 3, 4, 5, any positive number greater than 1, then those are also solutions. Okay, part B says, should your four values also be solutions to the inequality x times the quantity x plus 4 greater than or equal to 5? Explain why or why not, and are they? So what they're doing here is they're taking this x squared plus 4x greater than or equal to 5, and they're factoring out an x on this side, leaving us with x times x plus 4 is greater than or equal to 5. Okay, so that's what they have here. So nothing has changed here in value. We just factored the left side. So the answer is yes. And it's simply because we just factored the left side using the distributive property. And so the two solutions you chose in A should still be solutions in B. Okay, part C. Should your four values also be solutions to the inequality 4x plus x squared? So all they're doing now is taking the 4x, moving it over here, and the x squared, moving it over here. And here you would say yes, commutative property. The commutative property of addition was done. Okay, so therefore the solutions are the same. Okay, part D. Should your four values also be solutions to the inequality 4x plus x squared? So 4x plus x squared. So we're looking at this equation. And then they subtracted 6 from the left, so it's minus 6. And then 5 minus 6 is negative 1. So yes, the answer is yes. They still should be solutions because we subtracted 6 from both sides. So what you do to one side, you do to the other. The inequality or equation would still be the same values for solutions. That is the subtraction property of equality. And now E, should your four values also be solutions to the inequality 12x plus 3x squared is greater than or equal to 15? So they're taking this equation again here. 4 times 3 is 12. X squared times 3 is 3. 5 times 3 is 15. So the answer to this is yes. We multiplied both sides by 3. So that would be the multiplicative property of equality. And you should always check your solutions in all of these as we're going, but they still should be true. Alrighty, page 2 brings us to example 1. What is the solution set to the inequality 5q plus 10 is greater than 20? Express the solution set in words, in set notation, and graphically on the number line. Okay, so 5q plus 10 greater than 20. Subtract 10 from both sides. 5q is now greater than 10. Divide both sides by 5. 5 is positive, so my inequality is still going to be greater than. So q is greater than 2. Okay. So now I'm going to, in words, q is any number greater than 2. Okay? Set notation. The set of all q's such that q is greater than 2. Close bracket. Okay? Number line. Okay, so here's my number line. And what I'm going to do is q is greater than 2. I want an open circle on 2 because I'm not including 2. There's no equal sign. And then I'm going to make that pretty thick. And how about that purple we're using? So then I would have this as my solution. So an open circle here and everything to the right. Okay, exercises 2 and 3. Now you try this, finish this page, pause the video, come back, see how you did. Okay, so here we go. So to solve this, I'm going to subtract 4 from both sides. And that's going to leave me with x is less than or equal to 3. So you could just leave it as that, but in set notation, it would be the set of x such that x is less than or equal to 3, and close the bracket. And then I would put a number line 0, 1, 2, 3, and less than or equal to 3 would be an open circle here. And then when I go to do my number line, or my arrow to fill it in, I should say, then it would look like so. Less than is to the left. So it's any number less than 3. Oh, I'm sorry, it's less than or equal. So this should also be shaded in. Okay, so there's A. B, m divided by 3 plus 8 does not equal 9. If I subtract 7 from both sides, then I'm going to get m divided by 3 is not equal to 9 minus 7 is 2. Multiply both sides by 3 to get rid of that 3. The 3 is positive, so nothing changes, but it's not an inequality. Well, it is an inequality, but it's not less than or greater than. So m cannot equal 6. Okay. Oops. Why did I subtract 7 there? I don't know. Where did 7 come from? I'm subtracting 8. Subtracting 8. M divided by 3 does not equal 1. Multiply both sides by 3, and m cannot equal 3. Okay, so it'd be the set of all m. So I'll just do this now, put a bracket, the set of all m, such that m does not equal 3. And it would look just like that. So then when I do my number line, 0, 1, 2, 3, 4. Actually, what I should explain too is when you do a number line like this, your solution, you can always put your solution in the center. So then if I did that, then my 3 would be in the middle, like so. And it can't equal 3, so that's an open circle. And then to graph this, it's just everything greater than or everything less than 3. So it would look like this. Going this way, should probably make that a little thicker, but that's okay. You get the idea. And then this. So this is what my number line should look like, my graph. All values on the number line except 3. Okay, and let's do C now. So I want to solve this. I always like to move the variable first, so I'm going to subtract the smaller of the two so I don't get a negative. Subtract 7y from both sides, that should be a y. And 8y minus 7y is just simply y plus 4 less than negative 2. And then subtract 4 and subtract 4, and I get y is less than negative 6. So putting this in set notation, you just do this. The set of all y such that y is less than negative 6. So as I said before, when you're graphing, you can put your solution in the center and just a couple of points on either side. Like so. Okay, there is no equal sign, so I put an open circle on my solution, and then I go up and I choose my number line. Let's make that thicker this time, and blue, and y is less than is this way. So my solution is all values less than 6, but not including 6. Okay, here's D. This is the distributive property, but if 6 and the other side are factorable, or if this is a factor of the other side, I can simply divide both sides by 6. It makes it much easier. That would leave me with x minus 5 is greater than or equal to 30 divided by 6, which is 5. And then I add 5 to both sides, and that will give me x greater than or equal to 11. So my solution, my set notation would be the set of all x such that x is greater than or equal to 11. Okay, so my number line will now be, okay, my solution was 11, so I will put 11 right smack dab in the middle and just show a couple more values left and right. So there's my number line, 9, 10, 11, 12, 13. My solution was 11. There is an equal sign, so that's going to be shaded. And I want greater than. Now, I never mentioned this before, but if you have the variable on the left, this symbol is pointing. Think of that as an arrow. That's the direction you're going to shade. Okay? So just like up here, let's go back. See how that is pointing to the left? My variable's on the left, and that is pointing this way. So my arrow is going the same direction. It doesn't work with not equal. Not equal points both ways. But this one, x is on the left, and my inequality looks like an arrowhead pointing to the left, so that's the way I'm going. Notice that, okay? They match. Okay, so we're going to do that here. It's going to the right. So I'm going to choose my arrow, thick, and black, and that way, just like that. Okay, and next one, let's do this one in red. We have a factor of 4 and a factor of 2, so the first thing I can do is divide both sides by 2. So if I divide this by 2 and divide this by 2, these 2's cancel, bring my greater than sign down, and bring down my x minus 2. And then over on this side, 4 divided by 2 is 2 times x minus 3 quantity. Okay. Now I'm just going to distribute 2 times x, 2x, 2 times negative 3 minus 6 greater than x minus 2. Now move all my variables to the left, and I'm going to get x minus 6 greater than negative 2, and then I'm going to add 6 to both sides. And when I do that, I get x is greater than 4. Okay, so let's see if that's all connected. It is. Now it's not. Okay, anywho, Control Z, undo. All right. Anyhow, so my solution set would look like a bracket here, the such that symbol, and then a bracket here. So it's the set of all x such that x is greater than 4. My solution was 4, so I'm going to put that there. 5, 6, 3, 2, no equal sign. Check the original to make sure. No equal signs, an open circle at the solution. Greater than, the arrow is pointing, think of that as an arrow, it's pointing this way, so I'm going to come up here, choose arrow, choose the thickness, choose the color, and you get the idea. And it's going to go like so. So open circle at 4, shaded to the right. Okay, page 3 brings us to problem number 3, and it says, recall the discussion on all the strange ideas for what could be done to both sides of an equation. We can add, we can subtract, we can multiply, we can divide, and so on. Let's explore some of the same issues here, but with inequalities. Recall, in this lesson so far, we have established that adding or subtracting and multiplying through it by positive quantities does not change the solution set of any inequality. We've made no comment about other operations. So part A is going to look at squaring. Do capital B is less than or equal to 6 and capital B squared less than or equal to 36 have the same solution set? If not, give an example of a number that is in one solution set but not the other. All right, so I'm going to do, let's see, so we have, let's change back to my pen, B is less than or equal to 6. Okay, so 6, 5, 4, 3, 2, 1, 0, all the way to negative infinity is true. But if I take b squared is less than or equal to 36, and I take the square root of both sides, then we get b less than or equal to 6, or b greater than or equal to negative 6. Okay, and let's check that. So if I put 7 in for b, 7 squared is 49. That is not less than 36. But if I put 6 in, it's equal. If I put 5 in, 25 is less than 36. If I put 4 in, 16 is less than 3, 9 is less than 36. If this was 2, 4 is less than 36. B is 1, 1 is less than 36. B is 0, 0 is less than 36, and so on and so on. But when I get to negative 6, negative 6 squared is positive 36, they're equal. But if I go less than negative 6, like negative 7, negative 7 squared is positive 49, and it is not less than 36. Okay? So an example of a number that is in one solution set but not the other, if b was equal to negative 7. 49 is not less than 36, but negative 7 is less than 6. Okay? So squaring does not make an inequality still true. B, multiplying through by a negative number. Do 5 minus c greater than 2 and negative 5 plus c greater than 2 have the same solution set? So let's see. 5 minus c is greater than 2 is my original equation. To solve for c, I'm going to subtract 5 from both sides, and that's going to give me a negative c. Do not forget your negative symbol. Is greater than 2 minus 5, which is negative 3. I don't want a negative c, so I multiply by negative 1 and distribute. Negative 1 times c is a positive c. Multiplying by a negative 1 flips the inequality, and negative 1 times a negative 3 is positive 3. So I need values of c less than 3, and I'll check. 0 is less than 3. 5 minus 0 is 5. 5 is greater than 2. Okay? Now I'm going to take that, and if I multiply everything by a -1, 5 becomes -5. Negative c becomes positive c. And 2 becomes -2, and leaving us with this equation. 5, or inequality. -5 plus c is greater than -2. If I solve this, I'm going to add 5 to both sides. And that will leave me with c is greater than 3. So if I chose 4, -5 plus 4 is greater than -2. Okay, time out. Sorry about that, a program running in the background crashed. Okay, so anywho, where were we? -5 plus 4 is greater than -2. Add 5 to both sides. Or actually, no need to do that. -5 plus 4 is -1. -1 is greater than -2, that's true. But is it true for everything? That's what we need to know. So let's try something else. C has to be greater than 3. How about 4? -5 plus 4 is -1. We just did that. How about 10? -5 plus 10. Oh, I see what I'm doing. This is true because this is what the equation came out to be. But notice over here, c has to be less than 3 to make it true, like 0. So 5 minus 0 is 5. 5 is greater than 2. But if I plug in 0 here, -5 plus 0 is -5. And -5 is not greater than -2. So there's an example. C equals 0. Okay, part C says bonzos, ignoring exponents. Do y squared less than 5 squared and y less than 5 have the same solution set? So let's check. So if I have y squared is less than 5 squared, that would be y squared is less than 25. If I take the square root of y and I take the square root of 25, I get y less than 5 or y greater than -5. Okay, so if I put that on a number line, okay, so there's my number line. Well, I want -5 over here, and I want 5 over here, with 0 in between. Y is less than -5 would be an open circle here, and greater than, and y less than 5 would be a circle here. So let's check 0. 0 squared is 0, and that's less than 25, so that's true. So I'm in the right vicinity. So now I'm going to shade this thick green, and so it's in between. So there's my solution set graph to give you a better picture. And so any value between -5 and 5 will work, but anything greater than 5 or anything less than -5 will not. But if I take this equation, y is less than 5, and I graph that on a number line, so if I had the 5 over here, then I'd have an open circle at 5, and then if I had 0 here and -5 over here, then my solution set would be less than 5. All right, so if I choose a line like so, and thicker, and blue, and drop that onto this graph right here, that's what it would look like. Now what I'm going to do now is I'm going to put this over on top of the other graph, which would be like so, and I'll put it above. And then my solution was also 5. Oops, let me just do it this way. I'm just going to put a circle here. So the solution, not 5 is true. 5 makes both of these false. 5 squared is not less than 5 squared. 5 is not less than 5. But other than that, 4, 3, 2, 1, 0, all the way down to -5 is true in both. But this blue arrow is telling me to continue beyond -5. So if y equaled 6, this is false. I'm sorry. I want to go beyond -5, -6. If y is -6, -6 is over here. That is in the solution set because this arrow says to continue this way. Okay? So -6 is here, and it's in the solution set for this equation, but not in this one. Negative 6 is not greater than negative 5. Okay, so the solution sets are not the same. All the solution sets in the squared are in the not squared, but there's more in the one that's not squared. Okay, on to page 4, example 2. Jojo was asked to solve 6x plus 12 is less than 3x plus 6. Okay, for x, she answered as follows. 6x plus 12 is less than 3x plus 6. So she rewrote the original, which is good. Okay, and then she factored out a 6 on the left, and she factored out a 3 on the right. That's true. Okay, 6x, 12, 3x, 6. Okay. But then she said x plus 2 is in both, so if I divide both sides by x plus 2, I get 6 is less than 3, or multiplied through by 1 over x plus 2 is the same as dividing by x plus 2. So she applied the distributive property, and she multiplied through both sides by this. Okay. A, since the final line is a false statement, she deduced that there is no solution to this inequality, that the solution set is empty. What is the solution set for 6x plus 12 is less than 3x plus 6? Well, if I solve this, then I would subtract 3x if I didn't factor like she did. If I subtract 3x from both sides, I'm going to get 6x minus 3x is 3x plus 12 is less than 6. Subtract 12 from both sides, and I'm going to get 3x. These cancel. Less than 6 minus 12 is negative 6. And then when I divide by 3, 3 is positive, so the inequality stays like it is. Negative 6 divided by 3 is negative 2. So in this sense, any value less than negative 2 is true. So the solution set is the set of all x such that x is less than negative 2. Okay, now B says, explain why Jojo came to an erroneous conclusion. Okay, the explanation to B is quite lengthy, so I just brought it in as text. Multiplying through by 1 over x plus 2 is dangerous, as we do not know whether or not 1 over x plus 2 is positive or negative, okay, or even well-defined. Negative 2 makes it undefined. Its value depends on the value one chooses to assign to the variable. We could potentially multiply through by a negative value, making the final step invalid because of the inequality not getting flipped. The property of inequalities allows for only multiplication through by positives. We do not know then if this step is actually valid. Things can and clearly have gone wrong. Okay, example 3 says solve negative q is greater than or equal to negative 7 for q. Okay, so if I have negative q is greater than or equal to negative 7, and I multiply everything by negative 1 because I don't want a negative variable, then negative 1 times a negative q is q. Negative 1 times a negative 7 is 7. But when you multiply an inequality by a negative, this sign right here gets reversed. So I have q is less than or equal to 7. Okay, so I bring in my number line to graph it. And remember what I said, it's not a bad practice to just put your solution smack dab in the middle, show a value to the right, a couple integers, and to the left. Q is less than or equal to 7. My solution is here on 7. It's an equal sign, so that's going to be a solid dot. And then I'm going to shade it the direction this arrow is pointing, right? Remember I told you? That's an arrow pointing to the left. So I'm going to come up here. I'm going to choose this, an arrow, thicker and redder. And it's going to go this way. So there's my solution set. Any value 7 or less. Okay, moving right along, page 5 brings us to exercises 4 through 7. These are exercises, so pause the video, see if you can do these, come back and check your solutions. Okay, here we go. Find the solution set to each inequality. Express the solution in set notation and graphically on the number line. So this is an inequality, and I want f by itself, so I'm going to divide by -2 because it's being multiplied. Divide by -2. And -2 divided by -2 is 1f. When I divide by a negative, it reverses my inequality to a greater than, and a negative divided by a negative is positive. 16 divided by 2 is 8. So when I graph this, I would have an 8 here, and then I just put a couple more on each side. 9, 10, 7, 6. It's not equal, so I'm going to open circle it, and then I go up, choose my arrow, thicker, redder, and here we go. I'm going to, what happened? I see what happened, okay. It doesn't allow me to, this gets in the way, so I couldn't do it. All right, so there we go. Clean that up a little, there we go. Open circle at 8, shaded to the left with an arrow over here. Okay, next one. B, -x over 12. So this is a -1/12. So I'm going to multiply this whole thing by -12. These cancel, leaving me with x. Multiplying by a negative flips the inequality. Bringing a -12 over here, think of that as -12 over 1. These cancel, leaving a -3 over 1. So it's x is greater than or equal to -3. I forgot my set builder notation on the prior question. So I will go back, and here's what it looks like. The set of all x such that x is greater than or equal to -3. And if I go back here, I want set builder notation here, my slash, my f, my bracket. F, the set of all f such that f is greater than 8. This one is the set of all x such that x is greater than or equal to -3. So my solution is -3, -2, -1. I'm just making my number line, a couple of values on both sides of my solution. It's an equal sign, so my solution gets a shaded dot. Then I draw my solution line, the direction, the color, and voila, there's my answer. All values where x is greater than -3. Part C. Let's change the color to blue. I'm going to subtract 6 from both sides first. And that's going to leave me with 0 minus a. I don't want to write my 0. Let me get rid of that. 0 minus a is just a -a. Greater than or equal to 15 minus 6, which is 9. Divide by -1. Divide by -1. And I get a less than or equal to -9. Put a -9 in the middle. One to the right, another to the right, one to the left, another to the left. Circle, look at your equation, it's got an equal sign, fill it in. We're going to the left because it's a less than. So, arrow, thicker, bluer, and it's in my way again. I don't know if I can, maybe if I click here, that'll get rid of it. And then I can use it. That'll work, okay. All right, so -9 and everything to the left. Next one, -3 times the quantity 2x plus 4 greater than 0. So I want to divide both sides by -3 to get rid of that 3 on the left. Canceling them, leaving with 2x plus 4. Dividing by a negative flips the inequality. 0 divided by -3 is still 0. Subtract 4 from both sides, and I get 2x is less than negative 4. Divide both sides by 2, and I get x is less than negative 2. Okay, obviously that's in the way of my number line, so now if I just move this up here like so, I have x is less than negative 2. I need to put that in my set notation. X such that x is less than negative 2. Let me go back and do that here. And a and bracket a, the set of all a such that a is less than or equal to negative 9. The set of all x such that x is less than negative 2. Negative 2 goes here. And notice how repetitious this becomes. And if you did all of these, you get really good at it, and it becomes simple. And then when you go to take a quiz or a test, it's a piece of cake. All right, so pick this. Thicker, purpler, and I'm going to the left. There's my solution. All values less than negative 2, but not including. All right, so now we have this property here. It says recall the properties of inequalities. Addition property of inequality. If a is greater than b, then a plus c is still greater than b plus c for any real number c. Multiplication property of inequality says that if a is greater than b, then some constant k times a is still greater than some constant k times b for any positive real number k. Now 5 says to use the properties of inequality to show that each of the following is true for any real numbers p and q. Okay, so let me extend the page here so this moves up a little higher on our video. All right, here we go. So it says if p is greater than q, then negative p is less than or equal to q. So what I want to do is prove this is true if this is true. So we already know that this is true. This is a conditional statement. The only time a conditional statement is false is if it is true, then false. So if I prove this to be false, this whole thing is false. If I prove this to be true, then this is true. So we're going to work on the right. In order to work on the right, I'm going to multiply the whole thing by negative 1. Doing so, a negative times a negative is positive. Multiplying by a negative flips the inequality. A negative times a negative is positive. Okay? That's one way to do it. All right. Another roundabout way, what we can do is we can take that first step that I just did and continue. Okay, so if I subtract q from both sides now, then I get p minus q is greater than or equal to 0. Okay, then if I subtract p from both sides, then I get negative q is greater than or equal to negative p. Okay, so it's the same as this, but now the q comes first, and the inequality is still opening towards that negative q. Okay, either way. Next one. So if I divide this by negative 5 and divide this by negative 5, I'm going to get these to cancel. I'm going to get p is less than, these cancel, q. All right. So now I want to see if I can get this on the other side. So I need to multiply both sides by 5. So in doing so, if I multiply this whole thing by 5, I get 5p is less than 5q. Okay? Now I'm going to subtract 5p from both sides. I want to get a negative 5p on this side. So if I subtract 5p from both sides, I get 0 is less than 5q minus 5p. And then if I subtract 5q on both sides, I get negative 5q is less than negative 5p. So this negative 5q ended up over here. This negative 5p ended up over here. This was opening towards the negative 5p, and it still is. So then if I divide by -5 on both sides, or by 5, I get negative p is less than, I'm sorry, negative p is less than negative q. Okay, let me go back to this. I got that stuff out of the way too. So negative 5q is less than negative 5p. I can just rearrange this and write the negative 5p over on this side, but that would flip my inequality and put negative 5q over here. All right, so now once I do that, I have negative 5p is greater than negative 5q, and then I can divide by 5. And divide by 5, and that's going to give me negative p is greater than negative q. But then if I multiply by -1, then I would get p is less than q. And that's what we have here. Okay, page 6 brings us to part C. So it says if p is less than or equal to q, then negative 0.0 or negative 0.03 p is greater than or equal to negative 0.03 q. So to prove this, I would say p is less than or equal to q, our original on the left, multiply both sides by 0.03. So when I do that, I get 0.03 q. Remember, multiplying by a positive, we already know, nothing changes. Okay, but then if I subtract 0.03p from the left and the right, okay, then I get 0 is less than or equal to 0.03 q minus 0.03 p. Subtract 0.03 q from both sides. And when I do that, I get negative 0.03 q is less than or equal to negative 0.03 p. All right, so now if I rewrite this so that p is on the other side, then I have negative 0.03 p. Now I'm flipping this whole inequality, so this has to get flipped over as well, and I get negative 0.03 q, and that's what we have over here. Part D says, based on the results from part A through C, how might we expand the multiplication property of inequality? Okay, so what happened? Well, if we have an A and a B and we multiply by a negative constant, the inequality flips over. So here's what it would look like in verbiage. So we would say if A is greater than B, then some constant k times A is less than the same constant times B for any negative real number k. Okay, part 6, problem 6, it says solve negative 4 plus 2t minus 14 minus 18t is greater than negative 6 minus 100t for t in two different ways. First, without ever multiplying through by a negative number, and then first by multiplying through by negative 1/2. Okay, so let's do this. Never multiplying by a negative. So what does that mean? All right, so first thing I'm going to do is rewrite it. Negative 4 plus 2t minus 14 minus 18t is greater than negative 6 minus 100t. Well, the first thing I'm going to do is combine like terms. And I have a negative 4 and I have a negative 14, which adds up to negative 18. I have 2 minus 18, which is a negative 16t. So I just cleaned this up on this side. It's greater than negative 6 minus 100t. Okay, So the next thing I'm going to do is, let me think here. What should we do? If I add 100t to the other side and add 18 over to here. So in other words, if I add 100t here and 100t here, negative 16 plus 100 is a positive 84t, minus 18 is greater than negative 6. Okay, so I added 100t to both sides. Then I'm going to add 18 to both sides. So I'm going to get 84t is greater than 18 minus 6 is 12. Divide both sides by 84. Divide both sides by 84. Cancels. T is greater than 12 goes into 84 7 times. So it's 1 over 7. So t is greater than 1/7. So if I put that in set builder notation, it would look like this. The set of all t such that t is greater than 1/7. Okay, so I solved that without ever multiplying by a negative. But now it says to start by multiplying through by a negative 1/2 on the first step. So that would be negative 1/2 times negative 4 plus 2d minus 14 minus 18t is greater than negative 1/2. But I'm multiplying by a negative 1/2, so let me just follow the rule that we just came up with in the last step. The symbol, the inequality flips over. What did I just do? Control Z. Okay, go back to here. All right, so it was this way, now it is that way. So greater than became less than, and I put a negative 1/2 here, parentheses, negative 6 minus 100t. Okay, so multiplying through by a negative, flip the sign. Now I'm going to distribute. 1/2 times 4 is 2. Negative times negative is positive. Negative times a positive is negative. Half of 2 is 1. Negative times a negative is positive. Half of 14 is 7. Negative times a negative is positive. Half of 18 is 9. Okay, less than. Negative times a negative is positive. Half of 6 is 3. Negative times a negative is positive. Half of 100 is 50. So I get 2 minus t plus 7 plus 9t is less than 3 plus 50t. Combine like terms. 2 plus 7 is 9. Minus t plus 9t is 8t is less than 3 plus 50t. Okay. Subtract 8t from both sides, and I get 9 is less than 3 plus 42t. Subtract 3 from both sides, and I get 6 is less than 42t. Divide both sides by 42, and I get t. 6 goes into 42 7 times, so it's 1/7. So 1/7 is less than t. So it's a set of all t such that, oops, let me erase that, because if I undo, it'll undo it all. All right, so I want my bracket. There's my set notation. The set of all t such that 1/7 is less than t. That's the same as t is greater than 1/7, which is the same as over here. We can flip that all over. Okay, number 7. Solve negative x over 4 plus 8 is less than 1/2 for x in 2 different ways. First, without ever multiplying through, and then we're going to multiply through by negative 4. So it's the same as 6, pretty much. Another practice problem. Okay, cleaned up my screen a little, and here we go. I will use purple this time. So the first thing it says to do is solve for this 2 different ways. First, without ever multiplying. So if I have negative x over 4 plus 8 is less than 1/2, and I want to get x by itself, I would subtract 8 from both sides. I could do that. Or I could get rid of this fraction. So if I multiplied everything by 4. So let's do that. Okay, least common multiple. Multiply through by 4. It says to, without ever multiplying by through by a negative. 4 is not negative. So if I multiply this by 4, the 4's cancel. I'm left with negative x plus 8 times 4 is 32 is less than 4 times a half is 2. Okay, so multiplying by the greatest common or least common multiple gets rid of the fractions. Okay, so then I'm going to move the 32 to the other side. And that's going to give me negative x is less than negative 30. Okay, problem with this. I would have to multiply by a negative without ever multiplying through by a negative, so that did not work. Okay, so that's usually what I try first, is get rid of the fractions. That didn't work. If you copied that, it's okay. That's why we have erasers on the other end of the pencil. So then we're going to try something different. So if I have negative x over 4 plus 8 is less than 1/2, this time I'm going to just move things around. So I'm going to subtract a half from both sides. Let's try this. So I get negative x over 4. 8 minus a half. 8 is 16 halves. 16 halves minus 1/2 is 15 halves is less than 0. I'm going to add x over 4 to both sides. Then I will get 15 over 2 is less than x over 4. Then I'm going to multiply both sides by 4. Think of that as 4 over 1. And those would reduce to 2. 2 times 15 is 30, is less than, these cancel, x. So 30 is less than x, and I could rewrite this as x is greater than 30. I always like to have my variable on the left, especially when graphing, because this tells me the direction it's going on the number line. So there we go. We did it without multiplying through by a negative. And now we're going to do it by multiplying through by negative 4. So if I take negative 4 times negative x over 4 plus 8 is less than negative 4. Oh, my fault. That's greater than now. We're multiplying by a negative number. Sign flips. Negative 4 times 1/2. Negative times a negative is positive. The 4's cancel. I'm left with x. Negative times a positive is negative. 8 times 4 is 32. Greater than, negative times a positive is negative. Half of 4 is 2. Add 32. Add 32. And we get x is greater than 30. Same as here. So if I put that in set notation, boom, boom, the set of all x such that x is greater than 30. Okay, page 7 brings us to the end of lesson 14. Go do your problem set.